So, welcome everyone. It's a pleasure to have you today. We have the honor to have today with us Raquel Urtasun, who's the professor of who is professor at the University of Toronto in the Computer Science Department, and she's the founder of Waabi. She came especially from Canada today, actually yesterday evening, to share with you her research and give a talk on AI-first approach to revolutionize self-driving at scale. She also comes back to her alma mater, EPFL, to receive the prestigious EPFL Alumni Award that will be given to her tomorrow at the Magistral. We recognize with this award the world-leading expert she has become in her field that will transform tomorrow's mobility. EPFL counts for over 40,000 alumni now. They're spread around the world, and they constitute an incredible pool of talents who are EPFL's pride and their best ambassadors. EPFL alumni that I represent today thrives to offer its alumni a unique and international network, a lifelong bond to EPFL, and services to support them throughout their careers, while we try to engage them as much as we can also to support the development of EPFL and its future alumni. I would like now to ask Professor Fua to join me on stage to introduce our guest. Professor Pascal Fua received an engineering degree from École Polytechnique in Paris in 1984, and his PhD degree in computer science from the University of Orsay in 1989. He then worked at SRI International and INRIA, Sofia Antipolis, as a computer scientist. He joined EPFL in 1996, where he is now a professor in the School of Computer and Communication Science and heads the Computer Vision Laboratory where Raquel did her PhD in 2006. Thank you.
Thank you. So I'm honored to introduce Professor Raquel Urtasun, whom I have known for more than 20 years now. When we first met, she was a master's student at EPFL. She was trying to decide whether she would do a PhD, and fortunately she did. So she started a PhD, and then she fell in love with Gaussian processes, which are a well-known mathematical technique. And to this day, every time I use a Gaussian process, I think of Raquel. After that, she graduated brilliantly in 2009. Before that? Okay, whatever. She graduated brilliantly, went to Berkeley as a postdoc to pursue her passion for GPs. From there, she went to Toyota Research Institute and to University of Toronto, first as assistant professor, and then, of course, all the promotion to associate and full. And there, in addition to publishing lots of papers and continuing to do her research, she discovered another of her passions, which is self-driving. And I remember Raquel telling me at a conference that now she actually enjoyed all the many different problems that self-driving involves, and I'm sure she's going to tell us about this in her talk. So not only did he publish a lot, but she also became the chief scientist at Uber in charge of their R&D and working, of course, on self-driving. And then, fortunately or unfortunately, Uber decided to stop doing this. And Raquel, being Raquel, something that small would not stop her. So she left and started Waabi, her own company, to pursue her dream, which I imagine she's also going to tell us about. So without further ado, Raquel, please.
Thank you, Pascal, for the kind introduction. And I'm very, very excited to be here today. And I have so many great memories of being at EPFL. And it's amazing how actually 22 years has passed since I first started at EPFL. It's mind-blowing how time passes and how well I'm getting, I guess. And I was walking to come here, and I passed by Satellite, which was one of the places I love to be, particularly in my first couple of years, until I got really, really busy with my PhD, and then there was less of that and more of work, I guess. Cool. So it's great to be here, and it's great to see how EPFL is really transforming as well. There are so many new buildings, so many new faces. So much, happening, I think, here. So it's been a great visit so far, and I really look forward for the next 2 days when I'm going to be here. Cool. So today I'm going to be talking about, what we are doing at Wabi, which is, I guess, my new company, and in particular, how we are bringing a new generation of technology that, finally is going to solve self-driving at scale, and in particularly in the field of logistics. All right, so hopefully this works. Great. So I think that, we probably all agree that self-driving is really a very, very exciting problem to be working on. And it's technology that is really going to transform the world as we know it today. Right? We're going to have safer roads. We're going to provide transportation for people that today cannot move from point A to point B. We are going to bring a solution to the supply chain crisis that, with COVID, it's even worse, right? It's so difficult to get, deliver goods to your house, to your laboratory, etc., right? And what is very interesting is that, the only solution to a lot of these problems is really automation. So this technology is definitely going to benefit society in so many ways. So to tell you a little bit about the company, so we are basically, a new company really bringing this next generation of AI technology to solve self-driving for logistics at this scale. So I founded the company a year and a half ago, and maybe a clarification of what Pascal said. I actually left Uber before they wind down the project. But we are based, headquartered in Toronto, a very proud Canadian company, as well as we have offices in San Francisco. One of the things that is important when you want to become an entrepreneur is, that you need to raise funds, right, to bring your dream to reality. So this was really my first startup, and on the first day that I actually funded the startup, I basically stand in front of the investors and, with a deck and a team, and I told them, I want 100 million Canadian dollars, which is basically 83 million US, to bring this dream for the next couple of years, right? No experience, etc. I was very, very bold. I was told later on, but I guess very successful on that first round. It took only 2 months to basically close the round, have all the money in the bank, and ready to go. And it was the largest Series A in Canadian history. And this, reflects the excitement out there in the investment community about the kind of technology that we are bringing that is revolutionizing self-driving. We are laser focused on have to have the biggest trucks, right, Class 8 trucks that bring mostly drive on highways and that really move goods along our big highways, right? And what we are doing is something that, building a product that is ready to commercialize from day one. We are not here to build demos, as we've seen a lot of demos of self-driving. We are here to really bring this product to the market. And we have a full stack solution. All right, cool. So oftentimes people ask me, why trucking? Why not robotaxis? And during, I guess, my tenure at Uber, I worked in both programs, self-driving trucks and self-driving cars. And it became very clear that, the area where really this technology is going to make a difference early on will be in trucking. And there's really 2 reasons for this. The first one is business side, and the second one is respect to the technology. On the business, this is one of the most exciting markets still out there to conquer. There is a $1 trillion market right out there just in North America, right? How many such markets do you know? Probably none at this point, right? So there is definitely a lot of excitement in terms of, the economics. At the same time, the logistics, the transportation community understands that the only solution to this logistics crisis is automation. So they are all, getting ready for when this solution will be in order to, utilize it. At the same time, from a technology perspective, driving on highways is easier than driving on cities, right? If you think of, the complexity of the type of scenarios that you see on highways is more structured, right? So potentially it's easier to solve. It's obviously still a very difficult problem, right? The solution doesn't exist yet, right? But definitely is a solution that is simpler to develop than robotaxis, where even the problem of pickup and drop-off is really, really hard, right? I don't know if you guys have Uber or Lyft here, or the equivalent in Switzerland, right? But when you look at how they do, they drop and pick up passengers, more than 90% of the time it's typically an illegal maneuver, right? And this is something that self-driving vehicles cannot do. So it's actually pretty hard to even, think about how to solve that one problem. All right, so there is a significant opportunity on logistics. Right, cool. So where is the industry today, and why do we need this new technology? So we've seen significant progress since the DARPA challenge that is now almost 2 decades ago. But when it comes to commercialization, this technology is nowhere to be seen, right? You don't go out the door and then you see self-driving everywhere, right? This is the dream that we are trying to bring, right? And you probably are thinking, why is this the case? There has been, great minds trying to solve this problem. There has been so many billions of dollars of investment, right? But still the solution is very far from where it should be. All right, so let's look a little bit into what is the reason that this solution doesn't exist today. So in my opinion, the main reason why this is the case is the technology that is employed. When we look at, the mainstream utilized in the industry, the software stack, for example, is very similar to what was utilized during the DARPA challenge, which is 2 decades ago. It's a very hand-engineered approach. It's an approach that is divide and conquer. Basically, you take this very complex problem of you have as input, data. You need to, from the sensors, you need to output what the vehicle should do, and then you decompose that problem into many sub-problems, and then you task engineers with a very tiny problem in this complex system, right? And with the hope that somehow you are going to piece together all these pieces to make your final decision, right? So this technology doesn't scale. This technology is built for incremental updates. This technology is based on the fact that everything has to work well, and you have this cascading of mistakes. Is something that is going to have a very hard time to really be at the level of solving, all the situations that might arise on the world. Okay, so we need a different way to try to solve this problem, right? And the question is, okay, what is this different way? I guess something that will not surprise Pascal is that for me, what is important is actually to bring AI to the picture in a central role. Maybe one more thing to say about the current approach is that, it's very expensive, it's very slow to develop. And at the same time, one of the reasons that, or one of the main open questions is, how do you test that this technology is ready for deployment? And, how do you test so that you see where potentially your system has an issue? And if you look at the industry today, most of this testing is actually by just cranking miles in the real world. This means that, teams crank, several million of miles per year in order to see what is the next problem that they need to solve. This is very expensive. It's definitely not the safest solution, right? And the better that your system gets, the more that you need to drive, bigger fleets, more miles, etc. So this doesn't scale, right? So that's another reason why we really need a different solution to the problem, okay? So we're going to try to bring AI to have, a central, role in terms of self-driving, right? Right now, in the current approaches, AI is utilized to solve some of the small independent problems, right, but not as a whole. All right, so probably you are all thinking, or at least those of you that are excited about AI, you're thinking that, oh, Raquel is talking about this magic neural net that takes data from the sensors of the LiDAR, the cameras, etc., and comes out with the right solution, right? So I don't believe that this is going to solve it either. And the reason why is that, this is not interpretable. And, if the system does a mistake, you don't understand, like, why it is that it actually did this mistake. And for certain applications, this is not a problem. But for a safety critical system, this is definitely a problem because you cannot validate and verify properly the system, right? This is something that regulators will have a hard time saying that, yes, this system is something that you can deploy in the real world. At the same time, it's very hard to make progress because a black box approach, right, there is very little you can do, maybe change a little bit the architecture, but you have no insights in terms of how to improve this. And lastly, you're gonna need too many examples to try to solve this, right? So machine learning works by example, right? Here is the input, here is the desired output. And as a consequence, right, you're gonna need to provide, for example, examples of safety critical cases, accidents or near accidents, which is unethical to collect in the first place, right? You cannot just go in the real world and say, I'm gonna collect accidents so that my system can actually handle those, right? So that you can imagine how very quickly you get in trouble. All right, so what are we doing that is different than these two approaches? So what we're gonna do is create a new generation of technology, a new generation of AI algorithms that is gonna help us to bridge the gap and then go to the next level. And in particular, we are gonna have the characteristics of being end-to-end trainable, meaning that the entire system can directly learn from data, right? So we get the automation that enable us to do very, very fast progress, to also be able to have to build much more with less people. But at the same time, we're going to be interpretable so that we can trace back into why the system made the decisions it made, particularly if it decides something to be wrong, right? And this is going to be an approach that you can validate and verify, which, as I said before, is very important for these safety critical systems. All right, so it's going to be an AI-first approach, it's going to be modular, it's going to be interpretable, but at the same time, end-to-end trainable. The fact that it's end-to-end trainable also enables us to be able to learn much more complex functions, be better at propagating uncertainty, and be much better at generalization in terms of dealing with all the rare cases, the long-tail distribution of events that might happen as you drive in the world. Okay. And for those of you that want to, maybe one more sentence, a little bit more technical. So in particular, it's a new generation of algorithms that use deep learning, probabilistic inference, and complex optimization in order to make all this decision process, okay? So it was very important in order to go to the next level in self-driving to actually have innovation from day one in the company, okay? The other thing or the second aspect that is very important in our solution, and the other key differentiator, is our approach to testing. Right, instead of having a very large fleet and crank miles, right, all the time, which is, as I said, unsafe and very expensive, what we're gonna do is bring simulation to the next level. And this will be the other key in order to solve self-driving, okay? So I'm gonna talk the rest of the talk today mostly about simulation. I'm gonna show you a whole bunch of videos, okay, so that you are entertained, so pick up your popcorn, and I hope you like it. All right, so this approach is going to be much more scalable, much more affordable, and as I said, we can build with much less. Let me tell you a little bit about how simulation works today in the industry so that you can understand why our simulator is so exciting. So when you look at the industry, right, people are using simulation, but simulation is just a tool amongst many, many tools in order to try to test the system. And there is like 3 types of simulation that are exploited. The first type, they call it simulation, but in reality, it's not really much simulation per se, but what they do is that they replay logs that they capture by driving in the world, right? So you replay footage that you already captured, and then you look at whether your system will do something different than what they did before, okay? So in this case, the robot is like my robot over here, right? So the self-driving vehicle is just watching movies and trying to kind of output what would have done if I was in this situation, okay? So it's very, very passive. So the good thing is that you can test the entire system. The bad thing is that you don't understand the consequence of your actions because you're just passively watching something that was already good to start with, right? You capture some data, you didn't have an accident, right? You were driving well, and then you see whether you do the same or not, right? So this doesn't give you that much information once your system is actually relatively good performant. That's what they actually use a second type of simulation. Which this simulation is oftentimes called virtual simulation. And the idea is that you build scenarios of things that might happen in the world. Typically, these are simpler scenarios. And then you test only the motion planner, which is the box that basically decides what is the maneuver that I should do, given that I know everything about the environment, okay? How the environment is today, what are the things, as well as how are they going to evolve in the future, okay? So this is one step forward in the sense that now it's going to be reactive. It's like playing a video game, but I'm only going to test one part of the system, one small part of the system, motion planner. And the way that I test this is by giving perfect data, right? So that's also not great, right? I'm isolating into only a single component, and I have idealized inputs, right? So that will not tell me also how the system might degrade and how everything might be correlated, right? The mistakes that I make in perception, in prediction, in inferring the world will affect motion planners. So this kind of ignores that fact. All right, so again, that's not a great solution either. The third solution that they employ, this is typically something that we see a little bit in papers. It's not really mainstream in terms of the industry. It's more exploratory, but is the ability to use graphic engines to generate training data for perception. Okay, so you build these virtual worlds, and then you render them, and then you have the ground truth because you have created the world, you know where the things are, and you utilize this to train perception systems, to train and test perception, okay? Now, this is a different type of step forward, right? But the problem is that these systems are not realistic. These systems are created by hand, these virtual worlds, so it's not scalable. And there is a big domain gap, big difference between reality and real footage and what these simulators can do. So you also cannot really improve your perception system that much. You cannot really test properly the perception system. There is a big domain gap. So that's also problematic. Okay, so there is a few kind of simulation tools out there that people use, and in the industry, typically it's a combination of these things that every player might use, but nothing that can really replace driving on the real world. Okay, so let's look at what is the problem with this, right? Is that you have this pyramid where there is a bit of simulation, but there is much more of capturing real, really driving in the real world. Because when you drive in the real world, you can really test your system, right? Everything is reactive, and then you can see the consequences of your actions, right? So with the simulator, I'm going to show you the next slide, right? We're going to invert this, and we're going to be able to do most of our testing on the simulator, and then we only need a little bit of road testing on the real world to do validation and verification. And this is a huge change in the industry where we can really flip around how everybody does things, okay? All right, so let me tell you why the simulator is so exciting and what is so special about it. So as I mentioned before, we need to create a simulator that really mimics reality. What does that mean? It means that we need to create virtual worlds that have all the diversity and scale of the real world, right? We need to create simulations of the sensors that are super realistic so that the input to the system that we're going to test is the same as it will be in the real world. We also need to create scenarios of all the things that might happen, including all these rare cases, etc. And we need to do it in a way that is very, very realistic, that is immersive, reactive, so that we understand the consequences of our actions, right? And we do this all in real time and all automatic, right? That's the desiderata what you need. So how we achieve this is, a simple idea, but it's very powerful, which is that, well, if we go around and see the world, we can potentially clone it, right? And with AI, you can clone this automatically. And if you are able to do this super realistically, then you can create simulations of everything that you have ever seen. Every pedestrian, every vehicle, every part of the environment, right? Every area, say in Switzerland, that you ever drove in your life. Okay, so we build simulations by cloning the world, and then we're going to modify this world so that we can test many different things that never happened before. Okay, so it's a very, very simple but very, very powerful idea, right? So you get the scale, you get the diversity, and since it's an AI system, through automation, you actually can do this all at the scale, right? So that's mind-blowing, very different from artists in their computer generating some virtual worlds that are not super perfect, and then trying to test in this a couple of scenarios over there. Okay. All right, and so that's how you can totally transform the way that you do testing, but we can go one step further, which is we can use the simulator not just to test the system, but we can also use it as a training environment where the self-driving vehicle can learn to behave in safety-critical situations that otherwise would be impossible to collect in the real world. Okay, so that's the way that we can expose the vehicle to all the possible things that might happen, including, you know, accidents, etc. And it learns to react and handle those well. Okay, so again, that's a big step forward in terms of self-driving. All right, so let me show you this. So I'm going to give you some insights of how the simulator works, and I'm going to show you some videos so that you can see. All right, so it's a closed-loop simulator. What this means is that we're going to simulate the world. Given this, we're going to generate the information about how the sensors in the vehicle will have seen that world, given where we are in that virtual world, right? Then we're going to take an action, right, that is based on our autonomy system, right, the system that is driving the vehicle. And that action is going to influence everybody else in the environment that is going to react to us, right? And then we continue operating, you know, like this, right? Creating a new virtual world, right, that basically reflects what the actors do, create the sensors again, etc. Right? So now it's like, you know, really playing a video game that is like reality. Okay. Cool. So it's immersive, it's reactive, and we're going to do all this in near real time on the cloud at the scale in parallel, so that we have, you know, many worlds that we can test in parallel. All right. Cool. So let's have a look at you know, some videos. Hopefully this. Okay. Cool. All right, so I'm going to now demonstrate the simulator, a few of the capabilities with an illustrated example, okay? So that you see kind of what are the things that we can do. And I'm going to go one capability at a time that obviously we combine to create these things, right? So that you see how, you know, what is the, you know, our ability to do things in the simulation. Okay, so I mentioned before that we can clone the world, right, automatically. So what I'm going to show you now is how we can clone the world, and then I'm going to modify the world and then resimulate it so that you can see you know, how accurate the simulations are and the power of the simulator. And I'm going to show you this in terms of one particular type of sensor, which is cameras, because humans, we're very good at, you know, understanding cameras because it's like our eyes, right? If I show you LiDAR or radar, it's going to be maybe a bit more difficult for you to see the realism of those sensors because, you know, most of you haven't seen that ever in your life, okay? So let's look at in particular the camera simulations here. And what I'm going to do is I'm going to take a little snippet of data that was captured by driving a vehicle, in this case around San Francisco. And then I'm going to play and resimulate this snippet, okay? So on the left-hand side here is the original data captured by real cameras and LiDAR. And on the right-hand side is always going to be a simulation. Every pixel is simulated, okay? So the first thing I'm showing you here is our ability to simulate the static part of the environment. So what I took is that I digitally clone automatically this log. Now it's part of the simulator. Every actor is part of the simulator. And then I remove all the actors so that you can see just the static environment, okay? And then I resimulate it so that you see the realism, right? So it's very accurate, right? It really looks like I was driving in San Francisco where there was no traffic, which is kind of a dream, right? This never happens. All right, so let's go to the next thing that we're going to do with this. And now what I'm going to show you is I'm going to resimulate everybody that was in the scene. And for one of the actors, I'm going to make this actor do something else that's different from what he did in reality, okay? So again, on the left-hand side is the reality. On the right-hand side is simulation. And what I'm going to simulate now is that what would have, you know, how would you have seen this if the white car was aborting taking a turn and was going back now to our lane? Okay, so again, every single pixel is simulated, and you see that the simulator is super realistic, right? You could have maybe believed that this was actually real footage. All right, so now we can change, right? This is showing the capability that you can take something that happened in reality and modify how the actors are driving around, okay? Okay, next thing I'm going to show you is we can also incorporate additional traffic, right? In this case, I'm adding one more actor, right, to the scene, which is the second car on the right, on the right lane, right? This is an actor that wasn't there in the first place, right? So we can remove actors, that's the first thing I show you. We can incorporate new actors, and we can modify the trajectories of the actors, right? This is a very powerful concept, right? Because now with any actor that you ever capture can be part of simulations in this particular area, right? And then you can modify what everybody is doing to create whatever scenarios you are interested in testing, including the safety critical cases. All right, but we need to go, you know, one step further, right? And some of the other things I'm going to show you, or what I'm showing you now, is Now we're going to flip actors. We're going to flip who is doing what. Okay, so I'm going to take the white car, and it's going to do what the gray car was doing, and the gray car is doing what the white car is doing. Okay, and again, I resimulate the entire scene. Right, and you see that, again, it's very realistic, right? This could have been real footage. All right. Let's go one step forward or further, right? And I need one more capability for this to be really like the real world, which is I should be able to simulate the environment if I modify where I am with respect to that environment. Okay, this is what I'm showing you now, which is I'm going to switch where the camera is placed so they see in the scene, and I'm going to resimulate the same scene, but now I'm driving on the right lane. Okay, is this clear? No? So now we can actually, not only change where the actors are, but we can also change our viewpoint with respect to the world. Okay, so that we can, because when we're going to drive in the simulator, right, depending if it's a different, it's not going to be the same human driving, right? And the simulator, we're going to change the scenarios, etc. I'm going to react differently, and therefore, my trajectory is going to be different, so I need to resimulate the world from different viewpoints, okay? Which is my new viewpoint as I'm driving. So this is the set of things that you need in terms of to be able to do this next generation simulation, okay? And hopefully this was very illustrative in terms of what are the types of capabilities that you require, okay? And with everything, you need to be like super, super realistic. All right, cool. Now let me tell you a little bit about scenarios, right? So now we can clone the world and we can modify it. That's great. Now we have to decide what are the scenarios that I use in order to test the system, right? And again, these scenarios, what it means is that we're going to create situations, right, that are of interest, and the actors and everything within those situations are going to be reactive to us, and we're going to be reactive to them, right? And then every time I make an action, I will resimulate the sensors, I will pass it to the software stack, and then it's going to drive in this virtual world. So how can we create these scenarios? So we have a whole bunch of different ways to generate them depending on what we want to do. So in the industry, the generation of scenarios is either by hand with the system engineers, that is typically very, very cumbersome, or they use very simplistic procedural modeling automation techniques to create simple scenarios, very scripted. In our case, we have many different capabilities of ways to do this. We can create programmatic, so with a few lines of code, you have your scenarios. This is something that the safety team really likes to do, because they want to test specific things, very, very particular, right? So they want full control of what they're actually testing in a way that they are also very efficient. I showed you before that we can take something that happened in reality, import it in the simulator automatically, and modify it. That's another way. A third way that we can do this is by using deep generative models, right? So now they are AI models. We can generate, traffic situations that are realistic. We can also generate different map configurations, different characteristics of the actors themselves when they drive, how aggressive they are, the composition, whether you are very Texas-like and you have a lot of, say, trucks, things like this, versus, in other areas you don't have so many, etc. Right? So we have ways to create, an unbounded number of these scenarios. But this is actually not sufficient. You need something more. And what is this something more is that, well, now we can create exponentially many scenarios, right? Good news is that, that reflect all the diversity of the world, right? And I can utilize those to test my system. So that's great, right? However, when the system is really, really good, it's actually pretty difficult to find a scenario where you're going to make a mistake, right? And if I just have a fixed set of scenarios, I'm going to need millions, billions of these scenarios to see where the mistake is. Now, it's much cheaper than driving billions of miles in the real world, much safer. But still, I'm burning a lot of money from that nice Series A in terms of my cloud compute, right? I'm just basically giving everything to Amazon, Microsoft, or your favorite, right? So that's not a great solution either. So I need some extra automation in the way that we are bringing, the ability to understand our mistakes. Okay, and if this hopefully runs. So we're going to do this through adversarial AI. So what do I mean by this? Or adversarial scenarios is that now we have the simulator is an AI system. The thing that is driving the self-driving vehicle, right, the brain, is another AI system, right, our autonomy system. And they are going to play adversary against each other, right? And by playing adversary, what the simulator is doing, right, is basically building cases that with high probability the system will not be able to handle, right? It's like a teacher that is looking like, oh, you don't do very well parallel parking, let me find a parallel parking that is even more difficult so that you fail, right? So that's the game that they're playing, right? They're playing adversary against each other. And this can be actually done very, very simply in the simulator, where the simulator is running in closed loop. We have the evaluator here that basically tells us how well we are doing. And then the simulator is doing this evaluator to modify the scenario, right, such that this, when we look at the evaluator, it's going to have a bad objective, right? Basically, it's going to have a hard time dealing with that scenario, okay? And you can do this automatically, very, very efficiently, okay? Where now simulator is really playing, nasty, right, and trying to create all those difficult scenarios. So we use this, every day. This is the simulator that runs in production for us, right? Where every time that you land, a piece of software in production, it goes through a battery of tests and all this adversarial stuff. Okay, cool. All right, and something that maybe is important to note as well is that you need to be a bit careful when you use simulation, in the sense that you shouldn't overfit to your simulator. The simulator should have the diversity of all the things that might happen in the world, which means that you need to have diversity in terms of the behaviors of the different actors. Okay, and these actors can be, simple actors, can be distracted actors, drunk-like actors, right? And then you need to be able to sample from those, utilize those, so that you are not overfitting to only one type of actor. Okay, makes sense, right? You want to, no matter how the people are behaving in the world, because it's still going to be humans driving for a very long time, you can handle those situations. Okay, so you need to kind of marginalize across all these different actors. Cool. All right, so, and as I mentioned before, the last bit that we can do is train in the simulator, right? So for those of you that like reinforcement learning and other type of approaches like this, basically every scenario that we show to the software stack, since it receives information about how well it's doing, can utilize this information as loss function in order to learn to behave better. Okay, and this is every tick of the simulator, right, in an instantaneous manner. Okay, so this is very, very exciting because now you have the next level of automation. Okay. All right, and as I said, it's very simple, right? The evaluator just gives back feedback to Wabi driver. Wabi driver is the brain of the self-driving vehicle that basically is learning from the experience in the simulator, from what is doing well versus not. Okay, so now you can actually learn in the simulator. You can also learn in, mixture of the simulator and the real world. So it's very, very exciting what you can do with what we call Wabi World, which is our next generation simulation. All right, so the consequence of this is that I don't need to spend billions like our competitors in all these things, right? If you look at some of our competitors, their burn rate is more than $1 billion a year. Okay, $1 billion a year, right? For the development, right? We can do this so much more efficiently and so much faster with this technology. Okay, cool. That's where people are very, very excited. Okay, so with what I showed you today, what can we do? Very cost-efficient development, right? We don't need these large operations. Through automation, we can do much with less. Instead of, I'm trying to replace the humans so that our team, only does the really exciting, important stuff instead of, spending their time just chasing the tail of what the software stack is doing. So yeah, and you get much faster development because everything, the entire system tunes automatically, versus in the current typical approach, you will go one model at a time in order to make changes. It's much safer, right? We don't need to drive so much in the real world. And this is important because self-driving technology is not yet ready. So there is risk, quite a bit of risk associated with testing, right? And we want to definitely reduce that risk. I want to save lives, right? Not having problems. It's very, very highly scalable. The technology here, the simulator, the autonomy stack can generalize much better across different sensor configurations and placements, as well as across geographies, so that we can bring this technology and, and bring it to market across, many different geographies. So the industry is typically very obsessed with North America and the Sunny Belt, and in particular Texas. I want to build this technology so that everybody across the world can really benefit from it. And finally, it's highly flexible because thanks to the simulator, everything that we capture matters. With the rest of the industry, every time you change a sensor or something, all your footage and everything has to be thrown, right? All those years of, oh, but look, I drove, so many millions of miles. Yes, but you're not telling everybody that you don't use it. So that's not really a metric of how well you're doing. Here, because we can resimulate reality, we can resimulate any sensor, we can reuse everything that we have ever seen. Okay, so we don't lose by building next generations, by using different lidars, etc. And that's very, very important. All right, so I hope that you're super excited about self-driving, and in particular, the role that it's going to play in logistics. And these beauties over here, are more than just a dream. They're going to be on the roads super, super soon, and I can't wait to show you this. Thank you.
I have one, and then you can. Actually, I have two. And then I'll let you go. I'd like to revisit. So first, when we first met, we were both members of a graphics lab. Mm-hmm. So it seems that Raquel has returned to her roots. Mm-hmm. And at the time, we had numerous discussions about physics-based modeling, which I think I was more arguing for, and Raquel was already arguing for machine learning. Mm-hmm. What's the right? So 20 years on, what's the answer?
Yeah, great question, Pascal. And as you know, I love graphics, and so I guess I'm bringing that back. So the answer is neither AI nor physics-based simulation. It's a combination of both, and that's what we use for what I show you today. Physics, you can model with simple physics, reasonably well things, but it's not realistic enough so that you don't have this domain gap between reality and simulation. So you need something that bridges the gap in terms of the realism, and that's the AI piece. So our algorithms are physics-inspired. They're not exactly physics. They have some equations in there, but there is a lot of AI as well. And it's in this combination that is like super, super, I would say, robust, fast to simulate, and at the same time, you don't need to know a lot about the environment to create these really realistic simulations. If you only use physics, you will need to know the material properties of every single element of the environment. Also, a lot of the physical properties of the sun, etc. And that's extremely, extremely hard to know, right? And it will cost a lot of, also money and time to actually do this. For us, thanks to this combination, you can do, it's kind of the best of both worlds. You need to know just a little bit of the environment that we can automatically extract, and then, resimulate very accurately.
Okay. And one more thing, you said you were going to focus on trucks.
Yes.
But the talk you gave, so in what you described, what is specific about trucks?
Nothing is specific about trucks, which is the interesting thing, right? Which is everything here generalizes, right? But it's very important that when you are actually a startup, that you focus on one application domain. If you try to do too many, right, it's going to take you a very long time to get there, and maybe you will never get there. So it's important to bring a product to market to start getting revenue, etc. And we have these beauties, right, which is our testing platforms, which are, the biggest trucks, Class 8 trucks. So that's our physical, testing prototype, right? And that's what we, what we're very, very focusing on. And this affects, really which scenarios we run for the software stack. This affects our sensor configuration. This affects how we build a safety case. Okay. But nothing on the technology is specific to trucks. Yes.
Great talk. Congratulations.
Thank you.
How would you react if I were to say that you're realizing an instance of the metaverse of things. So my thought is that the metaverse for humans has limited applicability, probably lots of money, but for objects like trucks that can learn from each other by being immersed in a virtual world, that could be an amazing opportunity. How you react to my view of the problem like this?
Yeah. I mean, you can call it the metaverse, you can call it whatever, right? I think this is, a funny name these days. I call it simulation. So it's important to know that here, we are trying to do something that is gonna help us test and learn, right? So we are not trying to solve, what is in the mind of every actor that is on the simulator, right? So it's focus in terms of what this metaverse needs to do, but you can if you want to view it that way, you can view it that way. But this simulation, this is not also specific to self-driving. If you're in robotics, this will be like super useful for any type of robot that you have, because again, nothing in the technology is for driving per se. You can exploit this for drones. You can exploit this for warehouses. Surgical robotics and other things, you can employ, some of our algorithms. So I think there is a lot that we can do, and right now we haven't yet shown our trucks out there. That's why I can't show you yet. But publicly we haven't shown them, right? But we have shown our simulator, and it's been amazing how it's been incredibly received in the industry, but at large in terms of robotics, everybody wants a license of the simulator. So that's great to see. So definitely, a use case of the metaverse that makes sense.
Thanks for a great talk. So I have another graphics question. So the idea is to clone the real world, put it in the simulation, and then you can retarget what you've acquired to different situations. So one of the advantages of the physically based rendering approach is that you can change the lighting, change many aspects, and then everything works together. And so I'm wondering, in your current solution, how could you, for example, change the weather, change the lighting, or do you need different logs for different weather conditions and different lighting?
Yeah, great question. So we haven't shown this yet externally, sorry. Apologies, I'm such a CEO now talking versus the scientist. But you can manipulate things such that you can change illumination, you can change things like this. You can go to the level of changing shadows and stuff like that. So there are some of those great characteristics of physics-based, but without needing to, as I said, know every single little property of everything. Yeah, great question. For example, we can simulate rain without needing to simulate every single raindrop, right?
Hi, Raquel.
Hi.
Great talk. So I agree that it can go actually very far in simulators. It can do very many things more efficiently, even if they're feasible in the real world. So I wanted to hear your opinion about the things that you think we can't do in simulators, or they're going to be very difficult. Do you think there are any questions that eventually we won't be able to answer with simulators, or you think we can go all the way to the end?
I mean, we are driving a physical truck, right? So there are certain things like functional safety, etc., that you can do with simulators, right? And it's important that we still do validation, right, and verification on the real world. The simulator is not going to fully replace, but you can do so much more, right, if you have such a simulator, right? Things that you will never be able to observe in the real world, you can actually understand whether you can handle them. So we are not trying to fully replace the real world, but definitely get us much closer to what you will need otherwise, right? You will need millions of vehicles driving for many years, right, otherwise.
So do you have something like specific in mind, maybe like a perception or control-oriented example where you think that creating that functionality in the simulator is going to be too hard? I understand that in the end it's going to be a hybrid. I mean, nobody's going to believe or know it would be necessary to say that everything happens in simulator, there is no need to the real world. But then other than like a testing bed, and yeah, do you have thoughts around that?
Yeah. Let's see. There are things like, let's see, hardware in the loop simulation. I guess there is a simulation attached, but we are still, through hardware, right? So there are things like this that it's important that you still keep the hardware piece as well alive, not just everything virtual. And hardware-in-the-loop simulation means that, when you have a physical system, right, and you're driving this truck, the computer is in the truck, and the computer doesn't behave perfectly, right, in the sense that there is spikes and there is many things that can happen. So you need to be able to see how everything also behaves with respect to the behavior of that simulator, right? The behavior of that physical system. So there is hybrids like this that are important. It all depends into also how much you spend, for example, into your vehicle dynamics and vehicle models versus whether you need more control in the real world versus not. I think there is no limit per se, right? But you need to really close the gap in all these different things. But I think the thing that is important is that in the industry there is this concept or this notion of, I have a simulation for perception. I have a simulator for motion planning. I have a simulator for this one thing. I kind of divide the world into just little pieces. And that's not what you need, right? You need a simulator for the entire system so that you can actually do system integration and system verification and validation. And that's the big problem, which is, how everything has to be realistic to achieve this. So I think, yes, I'm going a little bit around myself, but I think you still should be able to create such a simulator. It's a question of how long it takes you to get there, and then how much you do in the physical world. But typically, you do more on the control side in the physical world than in the simulator.
Thank you.
Hi, Raquel. Thanks again for the great talk. Maybe following up Amir's question, in your example, you were showing substituting vehicles, right? Are you also looking at humans? I feel that it's much harder to simulate humans or put humans that have body language and they have social cues that we don't know how to simulate. So how can you deal with humans?
Yeah. Let's see. So we have reconstructed humans and simulated humans, with doing like different activities and things, right, that you can put. Humans are more difficult for two reasons, right? One is that they are articulated and deformable, right? So that makes one level of difficulty, and their intention, typically the way that they behave, is a little bit more random than when you're driving. You're quite intention when you're driving, although some drivers do all sorts of crazy things, right? So there's definitely a different level of difficulty, but definitely we simulate humans, and they are, is something that we need to do with their diversity and the craziness of what they can do. Now, you don't need to simulate all human behavior in order to simulate everything that you need for self-driving. So that's also important, right, to think about. Not all,
In fact, in the context of truck, I definitely see that you have less human interaction. But if you have a robot in a crowded scene or like a self-driving car around Paris, it's much harder to not consider humans.
In the I guess kind of robots maybe that you do, it's a little bit. You need to be more human-centric, I guess, in the simulator. So that's why I focus today a lot on the vehicles per se, not on the humans. But we still need to handle humans because, even on the highways, right? Somebody's stopped, there's an emergency. They are going to be behaving, potentially interacting with us. We need to be able to handle those. We still need to drive in surface roads and close to cities, right, or even in cities. So there is still, some of the stuff that we need to do there as well. But the complexity is smaller than, this is one of the reasons I don't want to start with cities, right? Because, people do all sorts of crazy things there.
Thanks.
So, thanks for your talk. I have one question regarding the representation of your world. So basically, you're creating the world such that you can modify it and create an infinite amount of scenarios. Mm-hmm. But how do you ensure that when you test your software, that you're basically testing on scenarios which are representative of the real world?
Yeah, great question. So typically, in the way that in the industry people do this, or they think they're doing this, is by creating these simple behaviors and interactions that come from the interactions that you see in the real world. For example, ACC into somebody in front of you, somebody cutting, in front of you, etc. And then you kind of vary those parameters, right? But that's still a small subset of the things that might happen. So for us, you can think of it as the notion of coverage, right? What are all the things that I need to simulate so that for this specific operation domain where the truck is operating, I cover the space of scenarios that I might see, right? And there are, I guess, things that you can do that. There's ways that you can do that. And then basically you need to show that what we are simulating here covers the space of what I can see, right? And you need to, capture that probability distribution and then be able to see that, or to show that when you're sampling the simulator, you cover all those scenarios. That's coverage analysis, I guess. Yeah, great question.
Hello.
Hi.
So in real world, you will have thousands of edge cases that occur very rarely, and some of them you really need to have billions of miles of real footage to just understand that they exist. And so the question is, how do you imagine to simulate things that you don't know as a human?
Yeah. So, I mean, this is through, I guess, our AI systems can simulate the scenarios that you don't necessarily see. Through adversarial, you can simulate things that might be difficult, which are, corner cases, typically things that are very rare, but they still happen. There is also the fact that, how do you extend what you see so that you can quickly understand whether there's something missing? And the industry today, is thinking that, I will drive my fleet and hopefully I will see the stuff, but that's never going to be big enough. But these days you have dash cams in every single truck, in every single vehicle. So the information exists. It's a matter of, can you actually automatically extract it and use it to create your simulation? So for me, that's the future. Great question as well. One more?
Thanks for the talks. I think more a question to the COUR. So I remember reading an article in 2016, where there was a lot of traditional automaker as well, probably your competitors, saying that in the next 5 years we will see more change in the car industry than since the beginning. Now, 6 years later, I don't think we are there yet. So to your point of view, why were we too optimistic at that time? So is it like the technology is still not yet ready, or is more legal framework which is missing, or whatever? And then the second question is, when will it come? You were mentioning it will be soon there, so when?
The billion-dollar question, right? When is it happening? So to your point before, I guess I'm going to be harder with the industry than you are, and typically we hear is 1 or 2 years away. Elon Musk is 1 year away every single year, right? And then he's never there. So this is, I guess, the combination of two things. The hype of, I'm going to tell my investors it's there next year, right? Which you obviously know that is not the case, but you're not going to acknowledge it. And second is, some people were overconfident of their abilities to solve the problem, right? And these two things together are pretty bad, right? So the industry has lacked accountability and transparency in terms of, really, you think that in a year you can put this? Obviously not, right? So this is something that I care a lot about, which is, no more bogus statements, right? And when we say that something is ready, we should really mean it, right? And when we give timelines, it should really be real timelines. Now, with the current technology, these traditional approaches, I don't think that's happening in many decades ever, or even ever, right? I think with this technology that I showed you today, you can go much faster towards that goal. But I think the one thing that people need to understand is that self-driving is going to be deployed first in small operation domains that are simpler, and then it's going to grow from there. So it's not going to be a switch that suddenly, oops, it's solved, and then there's, forget about traditional cars or traditional trucks, they are everywhere. It's not going to happen that way, right? And I think that's the other thing for people to understand, right? But the deployment into small operation domains is relatively soon, right? There is still a lot that we need to do in terms of how to prove that you are safe. Right now, there is safety frameworks, right? Safety cases that the industry has put out, but it is a lot of big words and no scientific way to actually prove it. this is something I really care about, to bring a scientific methodology into proving the safety case, which is, I think, one of the missing components so that we can really showcase and give peace to regulators that indeed this is ready. Now, in terms of is regulation an issue, depends on which country. Right now, for example, the States is the most open, I would say. There is 30-something states where you're allowed to test self-driving, so they are definitely open to help develop this technology. So that's, we are in a good position from that perspective. But we will see, we continue to work with regulators to make sure that they understand the technology, they understand what are the missing pieces, and they understand the path. But it's not just about regulators, it's also everybody, right, has to kind of embrace this technology and understand what it is and why it's a great thing to have it. So it's a very, very complex problem where you need so many areas, right, and everything has to come together. But definitely the fact that the consequences are going to be amazing, right? It's going to really transform in a positive way. It's bringing a lot of people to work together towards that goal. Right? But yeah, I hope to show you these trucks very, very soon and really deploy without driver.